from RG2 and 4 GR.
Thank you. So just in case, RG, that's Riemannian geometry, GR, that's general relativity. Thank you. My name is Olga, and I have my PhD in Geneva, for those who don't know. And I'm happy to be here with people who share the same issue. Actually, Donald, Elise, Friedrich, and me, we did PhD in Geneva, and not just in Geneva, but not just in space, but also in space-time at the same point. So we did it at the same time there, and Nikita, who is not here today, he didn't do his PhD in Geneva also at the same time. He was there at the same time for his postdoc. So it's like it's a very nice thing to be here together again, like an old gang. But now on the other side of the classroom. Okay, so I promised that this course will arm you with some foundations of differential geometry for what comes next. And next comes Friedrich in the afternoon. So our common goal is to understand the theory of gravity by Einstein. But the story actually begins 2,400 years ago. It is a warm summer evening in ancient Greece. Aristotle comes and he looks up in the sky and sees that something is happening. So he says, bodies are moving towards their natural place. Then Newton comes, looks up in the sky, gets hit by an apple, and he decides gravity is a force. So that's kind of the picture from yesterday is relevant for my talk a little bit. So he says space is populated by bodies, bodies have masses, and then gravity is the force of attraction between masses. And we lived with this theory for long enough, but then Einstein comes and he revolutionizes our understanding of gravity. Back to Aristotle. So he says, okay, bodies move to their natural place, but this natural place is defined by the geometry of the space-time. The space-time tells bodies how to move, and bodies with masses, they tell the space-time, the geometry of space-time, how to curve. So we are going to be in this framework. Now, geometry is gravity. Space-time is gravity itself. I'm going to walk you as gentle as possible through the right-hand side of this equation. Okay, it is a warm summer evening in the ancient Greece, and geometry is measuring Earth. We are interested in splitting land into some rectangular shapes. We are interested to know the distance between 2 points. We are interested to measure the length of a triangle, for instance. And let us start with a warm-up example. So how do we measure? And we start with some linear algebra. So we have a vector space, which is finite dimensional. And we define a bilinear symmetric form on this vector space. has the following properties. So it is non-degenerate. This means that this symmetric bilinear form is equal to 0 on two vectors for all vectors W in V. This implies that the other vector is 0. And it is symmetric. So this means G of VW is equal to G of WV for V and W in the vector space E. So an example is scalar product on vector space. The usual scalar product that we know. I'm assuming summation over the repeating indices here. Okay. So, and we say that this is a linear form which takes two vectors, so it goes from V cross V to a real number. And we define the following properties. So we say that it is positive definite. If this object on two vectors is larger or equal to 0 and negative definite. If it is less or equal to 0. With this form, with the scalar product on a vector space, we can define a length of a vector or a distance between the vectors. So our definition is for a vector in V, we have the norm of a vector, which is equal to the scalar product of this vector with itself. And then we take the square root. If we want to take distance between two vectors, we take the difference of the two, and then again we find the scalar product of this difference with itself, take the square root, and we find this distance. So this is what we have in vector spaces, and this is what we can actually do in Euclidean space, which actually we believed earlier, not we, but people before us, the Earth was. So we were kind of using this formula for our Euclidean space. 3. But now what is happening? We say that space-time has certain geometry. Geometry is gravity. So we basically want to generalize the scalar product to a smooth manifold. And here Riemann comes, looks up in the sky and says, let there be metric. Definition. So we say that a Riemannian metric on a manifold M is a type 0, 2 tensor field which satisfies the following at each point. At each point on the manifold. So there are two conditions. So the first condition is that this bilinear form taken on two vectors is symmetric. And then that it is non-degenerate and positive definite. Okay, we say that vectors v and u. Okay. So I count that you know that a manifold, a smooth manifold, is locally still like Rn. It means that at every point we can consider tangent space, which will be a vector space, and we can define such bilinear forms on every tangent space. So at each point, if we take two vectors in the tangent space, this bilinear form on these vectors will be symmetric, and then if we take this generalized scalar product of a vector with itself, it is always larger or equal to 0. So it is positive definite, and it is 0 only if the vector itself is 0. So this is a tensor, and tensor means multilinear map. In this case, this is a bilinear map from the tangent space cross tangent space to a number. So I keep writing down that we look at the scalar product at a particular point in the particular tangent space, but then eventually we will talk about tensor field. This means that we assign smoothly the value for such a tensor at each point on the manifold. So I will use some kind of, by language abuse interchangeably, words tensor, tensor fields, vector, vector fields, and G at point P, or just so it is a symmetric bilinear form on the tangent space at point P, and it eats two vectors and gives away a number. But as an object itself, it is a tensor field, and it lives at the dual space to that. All right, I didn't want to right on the last line, but still I did it. Right, in local coordinates, we take a chart and we take a point. We say that the basis for, say, like this. So that's the basis for the tangent space. And the dual basis for cotangent space, let's say that it looks like this. So then we can write a metric. In the following way. So here we have a smooth function depending on the point, and again I assume summation on the repeating indices.
So now you mean a tensor product of these things, right?
Yeah. Okay. Also we. So we have two basis elements here. That's what it means to be of rank 0, 2. So there are no bases coming from the tangent space, but there are basis vectors coming from the cotangent space. So that's an object in cotangent space, tensor with product with itself, okay? And it eats up two vectors to give a number. So what it means, let us calculate it on the basis vectors. Right. So this means that we have the coefficient, say G below, dx mu. In our bi-interior product, we contract the one form with the vector field, with the basis vector field. So, and this gives us delta lambda mu and delta rho mu, which produces this. Example. In physics, it is very common to define a metric by giving an element of length, infinitesimal length squared. So say that z squared is equal to g mu, x mu, dx mu. Okay? And here. No, I'm not going to write it in one. Then we have a matrix defined by this. So we have this squared equal to dv squared plus 2 dv squared plus 2 du dv. So from here we can read the coefficients of the metric. It's not diagonal, but we remember also that it has to be symmetric. So this part we just divide by 2, and we write down the metric. We can write it down. The metric coefficient is matrix. 2 by reading of GUU here is equal to 1, GVV is equal to 2, and GUV is equal to GVU is equal to 1 as well. Okay. So that's an example. Well, so far we speak about Riemannian metric. The manifold which has a Riemannian metric is called, a finite manifold with a Riemannian metric is called Riemannian manifold. And such manifolds are almost completely of no use in general relativity. So we are going to study something else. We actually need pseudo-Riemannian manifolds. What it means. From some physics courses, you have probably seen already the metric, which is not positive definite. So we are allowed for negative eigenvalues. So this is what it means to be pseudo-Riemannian. So definition. A tensor field again. So what we are going to replace condition 2 by something else. So we are going to allow for negative eigenvalues now. So a tensor field of type 0, 2 is a pseudo-Riemannian matrix. And then we will say that the manifold with the smooth manifold with such a matrix is pseudo-Riemannian manifold. If it satisfies the following conditions. So first of all, it remains symmetric. So all the other properties remain. It is a bilinear symmetric bilinear form defined on the tangent space. But the second property now becomes that this generalized scalar product of two vectors u and v is equal to 0 for any vector u this implies that vector v is 0. So the metric is non-degenerate. We can find, so the determinant is non-zero. We can diagonalize. We can find eigenvalues. We can diagonalize. And there are two important characteristics: the index and the signature of the metric. Somehow I cannot come up with an example which where one of these characteristics is more important than the other. So to me it looks like, right now on the top of my hand, that they're interchangeable. But let me tell you that the index of the metric of Pseudo-Riemannian metric is the number of negative eigenvalues. So, and then the signature, taking a list of the signs of these eigenvalues. Gently with 4 dimensions. If we have a signature like that, we say that the manifold with such a matrix is Lorentzian. So we have here index equal to 1. We have one negative eigenvalue. If we have signature with all the positive eigenvalues, we have Riemannian manifold. And then the flat metric, so to say, this means that when we can diagonalize the metric, by the way, sometimes there is a different convention in general relativity or in quantum field theory. For some reason, they always take different quantum field theory and general relativity, maybe to underline that they are incompatible, but so you could have the opposite thing. You could have here plus and then 3 minus 1. Okay? So this would be actually the same Lorentzian manifold, but in this case, you count positive eigenvalues to define the index, just to let you know. If you haven't had these metrics yet, prepare to be confused about the signature of the metric. So if you have a metric like this, so you have it in diagonal form. So then you have Minkowski space. So if your metric is identity, so in here you sometimes use the fancy letter eta, here you use the fancy letter delta, so that's Euclidean space. So that's for the signature and for the metric. And since, as I said, the metric is non-degenerate, the determinant is non-zero, we can find the inverse. It always exists.
So you mean this globally, right? For the definition, or
yes, that's globally.
Mm-hmm.
So the inverse. So we can look at this at the coefficients as at the matrix, as I said. We can find its inverse, and we can define a tensor of rank 2, 0. So in notation, this satisfies the following condition. If you take these coefficients, so G mu with low index, G mu with upper index, this is the inverse. You, sorry, no, I'm doing this. Lambda, you get, this is the same as the other way around. Lambda mu G mu, this is equal to delta lambda mu. That's the definition of the inverse. And then you can define tensor of rank to 0. Okay, so this time you have a bivector. And this guy takes two one-forms. So he takes two objects from the cotangent space. And gives away the number. Okay? And itself, it lives in the dual space. So in tangent space, tensor with tangent space. So and the metric defines scalar product of vectors. The inverse, the dual matrix, defines scalar product of covectors or one-fourth. Should I continue? So now there are two things. One is happening in physics and one is happening in mathematics. And they are essentially two sides of the same thing. So when we say that we can raise or lower indices with a metric, that's the physics language. In mathematics, we can say that there is an isomorphism between the tangent space and the cotangent space. So and the metric defines this isomorphism. If we have some vector, we can lower the indices and get a covector. So that's lowering an index. And then we say that here this we have a map. So we have this scalar product with a particular vector, which takes a vector and gives away a number. So it takes vector v, gives away g of u v, and we say that this is actually, we associate to it a one form. Omega u. So that's what one forms do. They take a vector, if you contract a vector with a one form, and they give a either a number or a function. Here in this case, we get a number. And this one form is taking vector u is equal to g u v. So this is how lowering indices works. The same we have for raising indices. So we can take an inverse metric. We can take a covector. And this produces a vector. are there people in the classroom who haven't seen tensors before, ever in their life? Okay, don't be shy, please. All right, so then probably all of you except one person in the classroom will be bored. But I still will remind you of some properties of tensors. First, physics definition. Tensor is something that transforms like a tensor. So that's just nothing more. That definition goes as follows. A tensor, or I will speak about tensors which values assigned smoothly at each point of the manifold. I will speak about tensor fields. So a tensor field of rank P plus Q and type PQ is a multilinear map by the way, how many mathematicians are in the classroom? Can I ask you? Okay, approximately half. All right, so then there is a chance that physicists haven't seen a mathematics definition, right? So it is a multilinear map which goes from CM tensor product to CM, okay, how many Q times, and then P times with the tangent space, P star M. So, and it has particular transformation law. Particular transformation law, I will specify it in a moment.
Excuse me.
Yes?
What's it mapping onto?
What?
What's it mapping onto?
You map to somewhere.
Ah, yeah, you have
There is a map.
T takes.
He goes from there to where?
Ah, okay. Okay, with a particular transformation. Law that was physics definition transformed as a tensor, and it is itself as an object of the space dual to that. It lives in Q times cotangent space product with itself, tensor product with itself. And P times tangent space. So, and it eats Q1 forms and P vectors and gives away a number. Okay? I'm going equally slow with physics stuff and with mathematics stuff, so I will probably annoy everyone in this classroom. I hope my expectation is not to lose anyone. And in coordinates, transformation law. It always occurs. So we have n-dimensional manifold. We change the coordinates from x to z. Then we have a tensor with a certain amount of indices. By the way, there are also, for upper and lower indices, there are also fancy names in physics, covariant, contravariant, probably they are used in mathematics as well. I never remember which is which. If you manage, then good luck. So we say tensor is, instead of saying that of type PQ, we say it's P times contravariant, Q times covariant, or the other way around. So just to know what it means. Then so here we tensor products. So all these looks very confusing. If you are fine with indices, that's fine, good for you. If not, there are plenty of exercises with the indices. I'm not going to do them on the board because this is just to write down the definitions, time consuming. To write down the entire exercise, just go for it and train. There is nothing conceptually difficult, it's just being attentive and work through all the indices carefully. So, okay, we have such a tensor, and then we change coordinates from x to z, and we obtain the object which looks like this. We again obtain the object which is PQ type tensor. So that's the point. This is what it means, tensor transformed like a tensor. You do coordinate transformations, you get a tensor again. And in physics, especially, we are very interested in such quantities because we want to write down an equation and we want to write it down in the same, want it to look the same in the, no matter what coordinates are. Okay. So, this will be a different coefficient here. The coefficient transforms, but then the rest of it in the other coordinates looks the same. We have gz1, gz2, and the transformation law transformation law goes as follows. For every index, you get a Jacobian matrix or its inverse. So you, okay, I will give you an example later. So you have gz I1 dx j1, then gz ip dx jp, dx letter, we recover a different letter, dx1 dz j1 and dx q Z J Q multiplied by the old coefficient L1, LP, and then NP. So this is the transformation law. This is quite bulky, but you can see if you write down a tensor. So that's an exercise to show that that's true. Prove that this is the transformation law. You take a tensor which looks like that, you apply coordinate transformations to every coordinate, this is what you get. Right?
Is this a good time to make a
Let me see. All right. Okay. So we stay with the definition. You meditate on that. And you can come up and take the exercises. And if you are bored during the break, you can think on exercise 1. Okay, let's keep going. Now, examples. So, tensors of rank 0, and these are scalars. And with coordinates change, they do not transform. Then tensors of rank 1, type 1, 0, these are vectors. We have a vector Ci d dxi, and then Ti, when we do the coordinate transformation, the components Ci transform as Zi dxi. Okay. Then you have the same thing for tensors of rank 1, type 0, 1. So this is 0, 1. These are covectors or 1 forms. And you have this matrix inverse. Sorry. Yeah. I'm doing the bad thing too. So we call vectors I dxi and Ci transform as dx. J dzi Ci j. Then you have tensors of rank 2. Then first type is 0, 2. The example is the metric. So these are bilinear forms on vectors. j. And then for coordinate transformations, you have gi, j, tilde transforming as L, dx, I, dz. Again, you see for each index of the tensor coefficient, you get a Jacobian matrix or an inverse of Jacobian matrix, and this is in general what you get. So further on, I will give you just examples of tensors. So tensor of type 2, 0, and example is Poisson vector, bivector. It is antisymmetric or skew-symmetric. Usually write it down with the here exterior product for being antisymmetric. Then it can be type 1, 1. And it looks like this, so you have Cij, ddxi, dxj. That's the object. And as an exercise, you can derive the transformation law with the coordinate change. So recall what is a pullback. Pullback of a tensor of rank 0m. So be careful, it can only be defined for tensors of this rank. Otherwise, if you have a tensor of mixed type, there is no consistent definition how you move tensors from one manifold to the other. So you have a map. So you do it along a map. You have two Riemannian or pseudo-Riemannian manifolds. You have a map going from one to the other. So x is coordinate of M, and then it goes to f of x. And then the pullback of the tensor. So what happens, you have T star n, T star n product, tensor product with itself m times, and you pull back this tensor to the cotangent space M, tensor product with itself m times. and it is denoted by the star, which is up. So then we say that the pullback of such a tensor you write it down this tensor. Where you have coefficients of x, and then this basis element d x tensor x. So that's the general definition. We will see an example in a moment. And while I'm talking about this, let's say we have a manifold Riemannian or pseudo-Riemannian manifold N, and we have an embedding, some submanifold M. So it is, so the embedding is defined, is a function f. You have submanifold structure on M, as a submanifold of N, and then you can define, if you have a metric Gn on manifold N, you can define induced metric on the submanifold. The pullback induces a metric in components. So now we see an example for this formula. We have Gm mu nu. So this will be metric on M induced by the background metric. So here we have the metric on the larger manifold. Defined at point f of x. So this goes for the coefficients for the matrix itself. Okay, and then you see an exercise. So you have S2 to sphere embedded in R3. On R3 you have a usual Euclidean metric. The map the embedding is given by the following. So the coordinates on the sphere theta phi. Then you have the coordinates on the on R3. Sin theta cos phi, sin theta, sin phi, cos theta. And then you have to find out the metric on the sphere given by this embedding. So I will give you the result. So G theta theta on M on S2 This is 1. G phi phi minus 2 is equal to sin squared of theta. And then G theta phi is equal to G phi theta is equal to 0. So that's a very easy example. Do the calculations just to be comfortable with what is derived, what is go where, which components do what, and which metric is on which side. So here, remark. Manifold is Pseudo-Riemannian. Then pullback of its metric to a submanifold doesn't have to be a metric. It only defines a metric if this pullback has constant index. So when we have a Riemannian manifold, we will always get a metric like this. When we have a pseudo-Riemannian metric, we need to be careful about the map that we have and check if the pullback that you get is actually yes.
I'm just sorry. In M to N, did we assume them to be of the same dimension, or can they be any dimension we like?
N and M?
Yes.
So M, we can assume any dimension, because here I give an example when M is embedded in N. And this construction produces the induced metric. Okay, so M is a submanifold. Okay, probably I was not clear enough. And F here is an embedding. So the dimensions here are different, obviously.
The F that you gave for the exercise is mapping I2 to I3, so in 2. How do you define that?
S2 embedded in R3. So this is the embedding. So theta phi maps to these three coordinates. So these are the coordinates for R3, and these are the coordinates on the sphere. This is the definition of the embedding. This is the map. So, Riemann? Yes?
Sorry, could you just restate the definition of the index?
Index
Yeah.
is the number of negative eigenvalues
Okay.
of the matrix. Remark or an example of induced metric. Actually, when you get familiar with the principle of superposition, you don't have to choose. It will be example remark. Example. Okay. Action functional for a string from string theory. So I emphasize that string theory, these are not chords moving, chords of a guitar or anything. Not mechanics, but string theory. All right, we have a string moving in some n-dimensional manifold, which is space-time, and then it traces a surface while it lives in this space-time. So we say this is the direction tau corresponding to time. This is the direction sigma. And here we have some length L. Right? Then this surface is called worldsheet. And it is embedded into space-time. And this embedding provides for induced metric on the worldsheet. So when we write the action functional for a string, so what we have here, we have so some integral of which produces the area of this worldsheet. And then the equation of motions will minimize this area. What we have here, we leave from tau 1 to tau 2 in this space-time, have integral over the tau. Then we have here the length of the string. And we have here the determinant, the square root of the determinant of the induced metric. So we have space-time with the metric G, and we have worldsheet sigma with the induced metric G large. Okay? So, and this provides you with the area of the surface. So exercise. So here, sometimes in physics especially, people like to write down the minus. So the this is due to the fact that determinant is negative. We cancel this minus. I will just put this as a norm of this quantity. So this is positive. We take determinant. We take the positive value, we take the square root, and then together with d sigma d theta, we get infinitesimal surface area. Okay? So exercise show that this is an element of the surface. So this part, this does not have to be induced. So this is an example of induced metric. So this is just have to be the metric on the surface, and this produces you the infinitesimal element of the area, and this is the example of the action for a bosonic string living in 26-dimensional space-time. This is called Nabu-Goto action. All right, now I will write you down the yes.
Excuse me, I have a question about your remark. When you said that the pullback of a metric is only a metric if it has a fixed index, but it seems like I would need to actually like compute the pullback of this metric, and then like I don't know, is there a more practical way to see just from the map itself? Like, is it, for example, sufficient if f is an immersion?
I do not know. So this is the pullback you can define for any map. But to define pullback of a metric to be, and pullback of a metric you can do.
Yes.
But for the pullback of the metric to be the metric on the manifold, then this has to be of constant fixed index. But I don't know. Probably there is a way. I never thought about this. Probably there might be some.
So maybe apart from having a fixed index, probably you don't want there to be a zero there, like a zero eigenvalue of the metric.
Yes, yes. No, and you don't want it to be degenerate as well. Right? So I don't know. It is a good question. I cannot give an answer.
What can go wrong? Like, is it that the index changes along different points in the manifold,
Yes,
or is it that f is not an immersion? So like, when you pull back, you're supposed to like push forward the vectors, right? So that they are.
You can define this map, and on the at different points it will have different signature or different index. So it has to be the same index all over the manifold.
It makes sense, like in the end, but like it would be nice to have a criterion for f, right? Instead of having to actually compute for every single form if it has fixed index.
I think it must always work with embeddings.
Are immersions though enough?
I don't know.
Dann kannst du theoretisch also der Index bleibt.
So then the
I mean, you could take R11, like in constant space in 2 dimensions, and then what will not work is like a curve, and you restrict to a curve, and it will not work if at some point this curve has slope 1 or -1. Because at this point, the metric would be degenerate, and it could like pass from +1 to -1.
Yes, you don't want the degeneracy as well. Okay. All right. Now, crucial question. We started from talking about geometry of the space-time, but let's have a look. A metric should somehow define this geometry. Normally, it has all the information we can calculate from the metric what quantities we need. Taking the transformations or taking derivatives of the metric, second derivatives, and so on. We will see a little bit later. But normally we might look at the metric and say probably, well, it doesn't have, it's not diagonal. It has some weird structure. Maybe it is curved, and it is not always the case. So, for example, for R2, I can write down Euclidean metric which looks like this, right? Or I can go to polar coordinates, and I can write down, and my metric will be like that. So we know that this is a flat space as well, but the metric doesn't look quite flat. But the only thing that happened is the coordinate transformation. Geometry didn't change. Okay, and the question is, how do we know by the look of the metric if the space is curved or not? And here there is an exercise 3, that you have two metrics, Riemannian manifolds of dimension 2, and there is a difference. Everyone has exercises, by the way. Is anyone who don't? Okay, so exercise 3, you have two metrics which looks almost identical, except that there is one factor which differs. One metric you have 4 v squared, and in the other metric you have 2 v squared. And one of these matrix is flat, the other one is curved. And the truth is, just by the look at it, you cannot say which is which. So if I ask you how could I know? So, and we will see later how we can tell, how we can deduce this information from the metric. But here for the exercise, I can tell you that you can try to do some coordinate transformations and to bring this matrix, these two metrics from coordinates u and v to some coordinates x and y, and one of them will look like this and the other not. So at least you will be able to identify the flat space like that. For the other one, you will not be able to tell because maybe you just didn't manage to find the coordinates. You will not be able to tell if it's curved or not. But later on, we will calculate curvature tensor, and this will give us the information if the space is curved or not. But now you can meditate a little bit on the exercise and try coordinate transformations to figure out which one is flat. All right. So now, that was the end of the first lecture.
Now we move on.
On the curved space, or on the smooth manifold, put it in correct terms, we want also to be able to differentiate vectors, right? But this operation doesn't work quite well on a smooth manifold, because what happens? Like heuristically, on Euclidean space, when we take a derivative of a vector, so we have a vector v mu dx mu, and we take a derivative with respect to x nu. Okay, so let me write it down, which has muth component. Okay. So what we do, we take. So usually we compare vector at point x, or a function. We compare a function at point x and at point x plus delta x. So here for the muth component, what we have the vector, we take the limit, delta x goes to 0, the mu, at the point where you move component nu by delta x nu, and then you subtract the mu at point x nu, and then you divide by delta x nu. But here what happens? This definition, you have this difference between two vectors, but one is defined at point x nu, x plus delta x, and the other one is defined at point x. And on a smooth manifold, this could be two completely different vectors. So you can change the basis vectors, you can change the basis of the tangent space, and you cannot compare them. So to compare them, you need to take this vector v mu at point x, parallel transported gently without change to the point x plus delta x, and then you can compare them, and then take the difference. So in Euclidean space, it's quite clear how you do that. On a smooth manifold, there is no obvious definition for parallel transport, so you have to specify how you parallel transport a vector. Probably along a vector or along some curve. So that's problem number 1 on smooth manifold. Okay. So problem 2, when we want to differentiate, when we take, like usual, directional derivative of a tensor, we do not get a tensor. Or we get something else. And again, in physics, we want our equations to look the same independently on the coordinate system that we choose. So we want to take a derivative of a tensor and get back the same tensor of the same rank and of the same type. The coefficients might look differently, but you get, sorry, not of the same, it will not be of the same rank and same type, but you take a tensor, you apply differentiation, and you get back a tensor again. So this is what we want. And the usual derivative is not working for that, so we need something else. So we need to define new structure. And the structure is connection. So then connection connects. Connection parallel transports. covariantly differentiates. This will be our extra structure on the solid manifold. So definition. Define a connection, and I'm going to use the terms connection and covariant derivative as synonyms. So this is the case for the geometry we are talking about. This might not be the case when you work with gauge theories. You have a gauge field, and then this gauge field helps you to define the gauge field, which is a connection geometrically. You will define using it covariant derivative, but here this is the same. Connection, let's say, or a covariant derivative. So I denote it by lambda, nabla. So this is a map. Which takes two vector fields on our manifold and gives back one vector field. So in the meaning of this, that you take the covariant derivative of vector y in the direction of vector x. So, and this object, if you do that, this object will be a vector again. Or if you do this to a tensor, the object that you get will be a tensor. The end of the definition. So this is a map which satisfies the following conditions. So it is linear in both fields. So what does it mean? It means that if we take covariant derivative with respect to x of vectors y plus z, this will be nabla x of y plus nabla x of z. And it will be linear in this component as well. So if you take covariant derivative of, with respect to x plus y, of vector field z, you get again nabla x of z plus nabla y of z. Then if you multiply the vector field x by a function, you get function multiplying this covariant derivative of y with respect to x. And then if you take covariant derivative with respect to x of vector field multiplied by a function f y, what you get first, here this is some kind of a Leibniz identity. So you get, first you apply the vector field to the function. This is multiply by y, and then you take the function out and you apply covariant derivative to the field Y. So here f is a function of manifold and x, y are vectors. So on a chart, it is practical to define the action of the covariant derivative on basis vectors. So we have at some particular point, at some local chart, we have the basis, which is dx mu, and then what you get the covariant derivative with respect to d dx mu, with the mu's basis vector of mu's basis vector. So by definition, you know that you take two vectors and you get a vector. So what you get? You get some linear combination of basis vectors. So you get some vector and you can express it as a linear combination of basis vectors again. So you have something like gamma lambda mu. Okay? So you have these components, you label the coefficients by 3 indices, but these are the coefficients of the linear combination of the vector you get. And these components we call the connection components. They define how your covariant derivative or connection acts on basis vectors, and sometimes we call them connection by language abuse, or as you will see later, also by language abuse, this could be Christoffel symbols, if you have certain properties for these coefficients. Right, and then now we can calculate how this covariant derivative acts on any vector. Okay. So you can take vector, covariant derivative with respect to vector v of vector w. So this is an exercise to verify. You write down each vector in expanding it in basis components. So you get the mu. So exercise to verify that. What you get. Lambda. So, and here, this part is the lambda component of covariant derivative of w with respect to basis vector in dx. Not to confuse with the covariant derivative of the component w lambda. Okay. Right. Now, another exercise is to verify that on covectors the covariant derivative acts in the following way. So d mu stands here for dx mu, okay? Gamma lambda mu omega lambda. And then you can deduce that if you take omega here as a covector to be equal to dx nu, then you get minus gamma. So you see here that the sign changes. It's, for this term, if you act on vectors or on covectors. So gamma nu lambda dx lambda. Okay. And then another exercise, probably you have it on your sheet, is to generalize this action on a general tensor. Okay. So now,
Excuse me.
yes.
On your exercise, the indices don't add up as far as I can see. The first term you have a new lambda, and the second term all the indices cancel away. Maybe I'm just blind, I'm not quite sure.
You mean here?
One line above.
Here.
On the left term you have a new and then a lambda at the bottom, and the right term all your things cancel away, right?
First term is W lambda.
First term.
Like you have V mu, L, W.
This one.
To the right. First term in the bracket. I think that's the question. It's just basically a V lambda E lambda, right?
First term, W.
This one.
Yeah,
lambda.
this one.
new
This one is lambda.
Yeah.
Yes.
This one, exactly. This
Yeah,
lambda.
yeah, okay. So probably somewhere here is the same issue, but that's an exercise to verify indices. It's correct. So, and again, exercise, calculate where T is tensor of rank PQ. All variant derivative acts on a tensor. Then, an important thing to notice here that these gamma lambda nu mu, these connection coefficients are not tensors. And this is again to verify that verify the transformation property for gamma I jk. Notice that it does not transform as a tensor, but it does actually transform as a tensor in particular cases. When the transformation property under coordinate transformation, right? So when you have coordinate transformation which is linear or affine, then these coefficients will transform as a tensor, just because you have some parts of it which cancel out. But normally it is not a tensor, and we need to remember about this. And another exercise, and the thing to notice, is that when you derive this transformation property for gamma, for the connection coefficients, from these transformation properties you can say that this thing, if you have two vectors, that the covariant derivative of a vector with respect to another vector produces you a vector. Okay? So this you can also show starting from the coordinate transformation of connection coefficients. You can say that if you change coordinates in which you define your vectors and covariant derivative, again you get a vector. So far we were speaking about metric independently, we were speaking about connection independently. But actually when we have them on the same manifold and we want to to look at geometry, we want to probe geometry of this manifold, we want them to be compatible in some sense. And by compatible, I mean that metric defines scalar product on the manifold. Connection defines parallel transport. So if we take two vectors, parallel transport them along some curve, we want the scalar product between them remain invariant. And this imposes particular conditions on the metric to be, and on the connection to be compatible with the metric. Okay? So again, I will leave it to you as an exercise, because I don't know how much time do we have.
5 minutes for this lecture.
5.
Or we make break.
5-ish. Okay. So I will leave it as an exercise. So show the condition so if the scalar product remains covariantly constant, it means that we take covariant derivative of the scalar product of two vectors, and it has to be 0. So the condition and V is the tangent vector which goes along some curve when we parallel transport that. So this has to be 0, and this is the condition that we want the scalar product to remain invariant all over our manifold. So this implies the metric to be covariantly constant. What it means that the covariant derivative of the metric is equal to 0. So to do that, you write all these in components. You write down how the covariant derivative acts on various components. And then one thing to keep in mind, which I didn't say, that the parallel transport is defined by the connection. The definition of the parallel transport is that the vector is transported along some vector without change. So this means that this is equal to 0. Okay? That's the condition for parallel transport along tangent vector.
That's for all k. It's the base.
Yeah, it's
So
just a base.
for all k.
Yes, for all. But here, so there is, you can put another vector here, but here I say that I parallel transport my vector infinitesimally in the k direction. So that's the condition of the parallel transport, and this will help you. You just apply covariant derivative, you will get Leibniz rule, and then these things cancel out, and you will have what you have. Okay. All right. Okay. So probably this is a moment to take a break. So I started speaking that metric has to be, connection has to be compatible with the metric for our purposes. We define the equation, we define the condition that the metric has to be covariantly constant. And let's write down this equation in components in terms of connection coefficients. So we get the following thing. Again, an exercise to verify if what I'm writing on the board makes sense. Zero. So this is the equation. And then what we want to do, we want to somehow find symmetric and antisymmetric parts here and separate them one from the other. So what we do, we rewrite this equation with cyclic permutation of lower indices. So I will denote this by star. So I write the star plus the mu lambda plus mu lambda mu equal to 0. You can do it. Again, the exercise verify. Okay. So I take all the cyclic permutations. Again, I get on the left-hand side, I get some kind of equation, a similar equation. On the right-hand side, I get 0, and I add up the 3 equations. Okay. What I get is no, the first one I take with the minus sign. So I can do that. So these are just, so left-hand side is equal to right-hand side, equal to 0. I can do whatever I want with them. It will be equal to 0. So I take minus first equation plus the other 2 equations, and I get d lambda g mu mu plus d mu g mu lambda plus d mu g lambda mu plus tk lambda mu g k mu plus tk lambda mu g k mu minus 2 gamma kappa, then mu with the permutation gk lambda, this is equal to 0, where I introduced 2 new objects, the tensor k lambda mu and the tensor gamma, and then in the brackets mu nu. So the definition is following. K lambda mu is defined to be equal to gamma kappa lambda mu with square brackets. It means that gamma kappa lambda mu minus gamma kappa mu lambda. So this is an antisymmetric tensor, and this is torsion. Okay. And then this part, so it is antisymmetric in lower indices. The upper index doesn't have to be. Okay, and then gamma mu with round brackets. This is symmetric part. So this
Let's negotiate the indices. That's not my job, by the way, it's yours. Mostly.
Gamma kappa. Okay. So, and for reasons which seem quite obscure to me, we want connection without torsion. So we want symmetric connection. I had various arguments. I'm not convinced. And actually, there are theories of gravity, which I think one of them is Einstein-Cartan gravity, which considers connections with torsion. But for Einstein's general relativity, we kill the torsion mercilessly, and we say that our connection will be symmetric. Okay. So from here, we remove these terms, and we define Christoffel symbols. I'm going to use again the letters gamma, lambda, mu. Sometimes they are denoted in literature as like this. Sometimes you can see them like that, these symbols, connection components of symmetric connection. It means that gamma, kappa, mu are symmetric with respect to low indices. So then we call them Christoffel symbols. There is a lot of confusion. Sometimes you call Christoffel symbols, you might see it in literature, Christoffel symbols, the gammas that we had from the very beginning, which need not have to be symmetric. Okay. So we define that, and we can find out the symmetric part from that equation. So this means I want this. Okay. Again, an exercise to verify that what I'm doing makes sense. The metric connection, or the connection compatible with the metric, which is symmetric with these Christoffel symbols, with these connection components, is called Levi-Civita connection. Now I hope I will please some mathematicians in the classroom. Theorem. So the fundamental theorem of Pseudo-Riemannian fundamental, the word fundamental and pseudo together don't sound good to me in the same sentence. And it says that on a pseudo-Riemannian manifold, or a Riemannian manifold with non-degenerate metric, I will say mg, and don't generate. I say that the determinant is not equal to 0. There exists a unique symmetric connection compatible with a metric. Okay. This is Levi-Civita connection. And it is specified if we take some particular coordinate system by Christoffel symbols. J, and I remind you, the Christoffel symbols, in Christoffel symbols you have symmetry with respect to lower indices. Okay. So, proof is an exercise. Now I'm making some physicists happy, I guess. Theorems are fun. Actually, when I was a PhD student, I was a TA for Anton Alexeyev's course for quantum field theory for mathematicians, and I was asking him, okay, I understand why mathematics is needed for quantum field theory, why quantum field theory is needed for mathematicians. And he said, oh, that's elementary. It is needed to prove theorems. And that was, well, the first time I heard it, it was a bit shocking to me. So, but that is actually the case. So, okay, proof. So, it is an exercise, but the, okay, you take, how you go, you take the equation, you take the covariant derivative of the metric that it is equal to 0. So you expand it in components and you choose only the symmetric connection coefficients. And then the only thing you will get eventually is that it has to be Levi-Civita connection. Okay, and then you continue. All right.
So symmetric means torsion-free, or?
Yes. Yeah. Symmetric, yes, torsion-free. All right. Now, this is the end of lecture 2. And we have, yes.
Does this only work in finite dimensions?
Sorry?
Does this only work in finite dimensions?
Finite dimension?
Finite.
Finite dimension, yes, we are talking about finite dimension. For infinite dimension, well, there are no Riemannian manifolds, Pseudo-Riemannian manifolds. We have to go to some Fresher manifolds. I have no idea what is happening there. Some things might work, some things just break, and there is no way to define proper stuff. So we're not talking about infinite dimension here at all. Unfortunately, I would love to, but not today. And tomorrow.
Right.
Right?
Nikita.
Nikita is not. Nikita is not here. Friedrich, today? No. Okay. Not today. We agree on that. That's the end of the lecture 2, and we have nowhere else to go. Elise, please lock the room. We we don't leave when this well done. Okay. We move to the next. To the next object. Okay. Just for purely informational reasons, how much time I have if we
asking for a friend.
if we finished in time.
Yeah, let's say, what is it, 30 minutes-ish, a little bit more.
Okay. Okay. So what happens with parallel transport on a smooth manifold? In general, if you start with some point, you take a vector here, you transport it along some parallel transported along some path C. And here you find this vector after parallel transport. But fun fact, if you choose another path, in general, you get a different vector after you parallel transport it. And the thing responsible for this is curvature. So due to curvature present on the manifold, the parallel transport is path dependent. Okay? What else can be screwed up by curvature is that covariant derivatives do not commute in general. And actually, curvature measures by how much they do not commute. Define curvature apart from connection from covariant derivatives. So we define. We have what is called Riemann curvature tensor. Is a map from taking 3 vector fields and giving back 1 vector field. Okay. So we define it in the following way. We also might think about it as an operator which takes 2 vectors, operator dependent on 2 vectors and acting on the third one. And we have several axiomatic properties of this tensor. So first of all, it is multilinear. So it will be linear in each of the vectors. So you can take x1 plus x2, you can take y1 plus y2, you can take z1 plus z2. Then you have, I will just write it down for one argument. Sorry, no. X and y for x1, r of x2, y, z. Then it is antisymmetric in x and y. R of xy acting on z is equal to minus r of yx acting on z. And it is a tensor. So on, you use the definition, and all that will be equal, so this is an exercise. You know how covariant derivative acts when you multiply vector by function in any of its arguments, and you can verify that this produces so in coordinates, we can write down so we just use this property. And this is a tensor of type 1. So basically this means that you get an object of Ri, J, D, dxi, dxl, dxk, dxj. All right, so what else can we say about curvature? I will not go into much details here. There are some exercises to work on, indices to work on understanding of these components. What you can do, you can verify the following thing. Again, if you take in components with covariant derivatives with respect to basis vectors, and you will calculate the following object. So you have the quantitative covariant derivatives with respect to basis vectors. Apply to some vector. calculation, it is an exercise. So you apply covariant derivative, you use Christoffel symbols, then you get the following thing. Dk gamma I j minus dj gamma I j is acts on this vector plus gamma I and k gamma m lj minus gamma I and j gamma m lk, and this on this vector, and then minus gamma jk m minus gamma m kj minus, okay, again, to verify if my computation is correct. Jk m minus gamma m kj gamma I L m psi L. Okay. So you see here that this part is cancels if it is symmetric, right? So you can split what you get into the tensor Ri L K J acting on vector psi L plus Cm Kj covariant derivative with respect to basis vector M psi J. And again, we say that if our connection is torsion free, the only thing that we get is the expression for Riemann tensor in Christoffel symbols, looking like that. So it is composed in terms of derivatives of the metric and second derivatives of the metric. You can write it down in components, you can do the computation like this. It is long, very, very long. I'm not going to do anything here. The only thing I can suggest you to do, an easy thing, just to get sense of the things, so take the metric of R2 in polar coordinates. So if you have just Euclidean space with Euclidean metric, everything will vanish immediately. You will not get anything interesting. But if you get Euclidean space in polar coordinates, you will not have many components to compute, but you have some of them. So you can get the feeling. So you take dr squared plus r squared d theta squared. You compute. So the metric is 1 r squared, it is diagonal. So you have the g r equal to 1, g theta equal to r squared. Then you can calculate, there will be some Christoffel symbols which are non-zero, and then apart from these Christoffel symbols, you will be able to calculate the tensor in these components. Okay. What should you find? What should you find for the components of Riemann tensor in this case?
0.
Yes, you will find 0 because the space is flat. Okay, and this is actually how we can test that this place, if the space is curved or not. You can, if you're stubborn enough, you can take exercise 3 and calculate Riemann tensor for both metrics and see where you can find non-trivial components. For one metric, you will not find anything different from 0. For the other metric, you will find some non-trivial components for Riemann tensor. Okay. So this is the part in components. Okay. Right. Okay, one more object. Ricci tensor. So that's another Ricci tensor. And we defined it. This is a 0-2 type tensor. R mu is equal to R lambda mu. So this is Riemann tensor, Riemann Ricci tensor with this indices exactly. Okay. And scalar curvature. This is the trace of Ricci curvature. And this is sometimes called Ricci scalar. I will leave it for you to show the use of that in general relativity. And you can also compute, this is an exercise, compute Ricci tensor in coordinates using the Christoffel symbols. And one important thing here that it is symmetric. Okay, so basically all the formal stuff is finished.
I have a naive question. So, well, some of them do not know about the metric, or at least don't have to know about the metric. Am I correct? Like, you remember about the metric here when you speak about symmetry, but otherwise you can just define it as you wish, right? For any gammas.
The Riemann and Ricci don't need a metric, just a connection.
Right? But then for the scalar then you say, okay, now I'm in the Riemannian compatible. So I'm just blindly looking at the formulas, pun intended.
Oh, you mean that you can define curvature just apart from the connection? Yes,
Yes. So these are x, y, z. I only know gamma ij with no conditions. I can do the thing, and it still behaves well. Then the Ricci 2, right? Nothing forbids me to contract the indices. But then for scalar curvature, I need the metric.
Yes, you do.
At that point, do I ask gammas to be something or not? So probably I ask them to be compatible, at least.
So you ask to be you ask the metric to be compatible with the convention.
Okay, but I don't have to ask for torsion freeness.
Normally no. You.
Okay, but this yeah.
So
Okay.
that's the condition which is imposed here.
Thank you.
So that's what we. Wait a second. So the way it is defined for GR actually, so this is what we call the Riemann tensor. So this is here the torsion-free condition is applied already. So we'll pick this.
No, but for GR, I don't know. I mean, there are better specialists in the room. I mean, I have some religion why it should be symmetric, related maybe to geodesics, but
only by the
then
definition
it's another story.
you can.
Okay,
Just go
thank
on. You require for scalar curvature compatibility with the metric, and then.
Thank you.
All right. What I wanted to say here, there are some symmetries of Riemann tensor, which we can again prove as an exercise. to write down everything in components for now. So a kappa lambda mu is equal to r kappa lambda mu. So it is antisymmetric in the last two indices. Here it is symmetric to lower the index. It is antisymmetric in the first two indices again. And it is symmetric symmetric with respect to interchange of third and second and fourth and first and third. So the exercise to prove that, you can just take the definition in terms of Christoffel symbols and derivatives of the metric and show the properties, the computation validity. So, and then
You also have the cyclic computation.
yes. So that's, again, exercise. Prove it here. So first, Bianchi identity. So you have cyclic permutation lambda mu lambda is equal to 0. And then second Bianchi identity, that if you act as by the variant derivative, it gives you 0. Way. Size component lambda plus this is equal to 0. So that I leave you as an exercise. And then, what physicists love to do, compute the number of independent components. And in a moment we will see why we do that. Due to the symmetry properties, so from the first, we see that for m-dimensional manifold, the number of components will go to so you need to choose any two components with respect to which we are symmetric. So then the same goes for the second, and then all in all, you will get, due to the first anti-symmetry properties, you can also interchange pairs of anti-symmetric components, and then you will get something instead of n. So this is number of independent components. Instead of getting n squared, here you get what you get something like n plus 1. You take a pair out of this. So you have half n multiplying n plus 1. And then the first Bianchi identity, you get this anti-symmetry in the lower indices. And the thing is that for dimension lower than 4, this is trivially satisfied. So this condition does not give you anything. And for the case when M is equal, the dimension of the manifold is equal to 4 or higher, you get this, and this obviously vanishes for M less than 4. So the number of independent components for Riemann tensor eventually will produce you something like half, then 2 out of M, then 2 out of M plus 1 minus 4, and you get 1 over 12, M squared minus 1. So you get this number. Okay. And now what I want to do, so we defined Riemannian, observed the Riemannian geometry for an n-dimensional smooth manifold. I now want to set n equal to something. And this concept is very mathematical physics. You use dimension as a parameter, and you see and you vary this parameter, and you see at which value some phenomena starts appearing. And maybe you have a chance to study this phenomena at the easiest point, so at the lowest dimension possible, and then see how it evolves, what properties you can deduce from that, and what properties can you study when you go to higher dimension, and what actually changes. Right? So now I say I want to study gravity in one dimension. What's my geometry? So, what would you guess? What's the geometry in one dimension? What's the curvature? So you have only one dimension, you have only one value for all possible indices. You compute Riemann tensor. That's the only thing you get, and by anti-symmetry properties you get 0 here. Okay. So all one-dimensional smooth manifolds have curvature 0. Okay. Now, just for the pleasure of confusing you, so we study geometry of curves. We say that, especially in physics, you have velocity, which is tangent to the curve, you have acceleration, which is orthogonal, and you say that the norm of the acceleration corresponds to the curvature. It goes inside this curve. So you say that this is curvature. And you can even choose an orthogonal frame, which is called Frenet frame, and say that in the third orthogonal vector here, and in terms of that, okay, I will put you down some equations. Okay, there is this. So you take, let's say t is a parameter on the curve. You write down your equation. You have v a t. Okay, no, I choose s here as a parameter, and then I have the following system of equations. And here this theta tau gives you the value of distortion. So what does it mean? Here I have curvature, here the Riemann tensor tells me that I don't. Yes?
I think it's because it's not intrinsic on the right-hand side. It's an artifact of the embedding.
Yes, exactly. So if I'm one-dimensional, if I live in dimension 1, I have no way to distinguish vectors which are orthogonal to the tangent one. I have only one tangent direction, so I only see in that direction. So I don't see anything else. So this curvature and distortion is extrinsic. It comes from the fact that we are looking at this curve as an embedding into R3. So this is extrinsic geometry. It is due to embedding. Intrinsic geometry means that there is no curvature here whatsoever. Okay, now let's go dimension one dimension up. And here in dimension 2 we see some geometry appearing. So for instance, if we take a curve, one-dimensional curve, we can map it smoothly to a straight line in a way that the distance between every 2 points is preserved. When we go to a surface, when we go to 2 dimensions, even locally, we cannot map a patch of a surface into R2, into a patch of R2 in a way that we, in general, well, there are some surfaces that you can, but in general, a priori, you cannot map it in a way that you will preserve distance between every pair of points. So there is some geometry in theory, some intrinsic geometry. So let's see what happens here. So now, gravity or geometry in dimension 2. Okay, for the Riemann tensor, we have only one independent component. This follows, so you can calculate it here, saying that m is equal to 2, or you can use the symmetry, anti-symmetry properties of the Riemann tensor, and what you get is you actually have only this component, and which is equal to okay, and all the others will be either equal to it, or minus this component, or equal to 0. So you will get only one independent component. Of course, an exercise to verify what I'm saying. Don't trust anyone. What does it mean? It means that this component can technically be non-zero, and this means that there is some intrinsic curvature here. So there is intrinsic geometry which does not depend on your embedding. What does it mean that we have only one independent component? It means basically that our curvature is defined by the scalar curvature. We do not need anything else. Okay? And you can prove that this is an exercise, and this is this is an exercise. You can prove that the scalar curvature is equal to twice Gauss curvature for a surface, a two-dimensional surface in embedded in R3. Okay. So, and that was, I always forget what's the spectacular theorem of Gauss. Who could help me? Yeah. What's the meaning of this spectacular or no? So the Gauss said that the curvature of a surface does not depend on the embedding, it does not depend on its position, it only depends on the angles and distances that you can define on the surface itself. So it is an intrinsic property of the surface. So here in dimension 2, gravity is starting to appear, but it's still a little bit trivial since it can be defined only by the scalar. Okay, we go dimension 3. We'll go higher. Oh, by the way, just to give you an intuition. So for surfaces with constant curvature, so this is scalar, but this is scalar in each point, right? So it's still kind of a function. It varies through the manifold. But if you have constant curvature, meaning that it's the same value for all the points on the surface, so you can distinguish 3 situations, and probably this will give you some intuition. So you have I'm not talking about lengths of curves or about geodesics. I will leave this to Friedrich. But just to give you an idea, we think about the geodesic as the straightest line possible, or the shortest line possible between points. Okay, so you can have a surface like this. Oh wow! So this is negative constant curvature. And the geodesics tend to fall apart. Okay? When you start and you move in parallel lines are no longer parallel, they separate. Okay? Then you have zero curvature, this is flat surface. So the parallel lines remain parallel, and then you have positive curvature. Like on a sphere in geodesics, you start and parallel lines come together eventually. So that's the intuition about what curvature does with straightest line possible on surfaces. 2 more minutes. Okay. Dimension 3. Okay. The Riemann tensor has 6 independent components, and the Ricci tensor has 6 independent components. And in dimension 3, so scalar curvature is no longer enough, but Ricci tensor defines curvature completely. And then in dimension 4, Riemann tensor has 20 independent components. I think that corresponds to 14 invariants, scalar invariants. So you still have some invariants corresponding to curvature. There are 14 of them. And it is obviously not enough. Ricci scalar is not enough. Ricci tensor is not enough. So there is something special happening there. So you have gravity in 4 dimensions. And then the same thing, so the number of independent components goes up. You have more geometries when you reach the dimension. That's all what I wanted to say. Not all, but I will stop.
Well, probably we have 2 more minutes for a quick question, if there is any. Otherwise, yes.
And I leave exercise 12 to Friedrich.
It's not a tangent, but it's the Ricci tensor what gives you the Ricci flow.
Sorry?
Is the Ricci tensor what defines Ricci flow?
Yes. Ricci flat, yes. But it's Ricci flat. Yeah.
All right.
Yes?
In 4 dimensions, you said we have some extra curvature that is not contained in the Ricci. In GR, we said that these parts are in the Weil tensor.
Yes,
And
yes, yes.
we
That's
also-
the part where I stopped. But that's not all I wanted to say. But
I was just curious because then later on we linked the Weil tensor to propagating gravitational waves. And I wondered, does that mean in 3 dimensions there wouldn't be like propagating gravitational waves?
no, that's not the situation. So Weil tensor you associated with conformally invariant things. So it's just in 3 dimensions. The conformal metric will be looking slightly differently. So there is no Weil tensor, but there is something else.
All right. So,
And in sorry.
okay.
In 2 dimensions, every metric will be. Sorry.
Good. So let's thank Olga again, and then we reconvene at 4:15.